Welcome to Ask and Learn.
All right, so the first thing to note would be to use a fact from problem 52, namely that the total mechanical energy, we call that E mech, of a satellite is equal to -1/2 times g times mass of the Earth times mass of the satellite over r. And so in part A, you want to know what the fuel is, or how much energy is required from the fuel to launch the satellite into orbit from the equator. So in this case, you have initially you have kinetic energy because you're launching from the equator, meaning the satellite has an initial velocity because the equator rotates with respect to the Earth. The poles do not. So in part B, we don't have this kinetic energy for term. So anyway, here you have kinetic energy plus energy from the fuel, which is what we want, plus potential energy, gravitational potential energy at the Earth's surface, and that is equal to the mechanical energy. All right, so energy from the fuel, kinetic energy is 1/2 mv0 squared. We'll calculate what v0 is in a second. Energy from fuel is what we need, and gravitational potential energy is negative gme times small m over re, that being the radius of the Earth, and we set that equal to 1/2 gme m over r. R is re plus h, radius of the Earth plus height to which the satellite rises. And so fuel, energy from fuel is, let's take this gme m term common. That times 1 over re minus 1 over 2 times re plus h. Whoops. That'd be an h over there. Minus 1/2 mv0 squared, v0 velocity of the Earth. Now we're gonna find v0. So v0 will be the rotational velocity. So that will be the circumference of the Earth, 2 pi times the radius over the period, the time taken for one complete rotation. So this is 1 day, right? So 2 pi times the radius of the Earth, which is 6.38 times 10 to the 6 meters, over 24 hours times 3,600 seconds in each hour. What you get is about 464 meters per second for V0. Awesome. So we have E fuel equals G, which is 6.67 times 10 to the -11 in SI units, times mass of the Earth, 5.98 times 10 to the 24 kilograms, times mass of the satellite, 1465 kilograms, times 1 over radius of the Earth, 6.38 times 10 to the 6 meters, minus 1 over 2 times radius of the Earth, 6.3 times 10 to the 6, plus the height, 1.375 times 10 to the 6 meters. All right. And subtract from that -1/2 m 1465 times v 464 meters per second quantity squared. Put all of that mess into a calculator or wherever, and you'll find energy from fuel being 5.38 times 10 to the 10 joules, or about 54 gigajoules. In part B, the only difference is at the poles, you have no kinetic energy initially. No Ke initial. Therefore, negative gme m over re plus E fuel is equal to 1/2 negative 1/2 GME m over RE plus H, giving us energy for fuel as GME times m over 1 over RE minus 1 over 2 RE plus H. And so, as you can see, the kinetic energy term, 1/2 mv naught squared, is gone. And what you get is something very close to the last answer. It's 5.39 times 10 to the 10 joules. And that's it.